Salam Doctor, I'm Sia Hong, and today I'm going to perform a lab demonstrations on my lab 2, convolution. Convolution is an integral concatenation of two signals, and usually it involves the two signal which is xt and ht. And the mathematical formula can be represented as below. We can see that xt multiplied by ht and xn multiplied by hn. This is for the discrete time, and this is for the continuous time signals. And let us take a look on our questions. So question 2.1. Since doctor have said before, for question 2.1, we just have to execute the code and then show our output only. And therefore, I'm going to show my output for question 2.1a. So we can see that this signal is the X signal, and this is the impulse signal. And after being convolutions, we will have the YN signal. So this is the result. And again, this is 2.1b. This is the result. So for 2.2, the questions have given us this expression. Okay, this is the formula of convolution, and this is the X signal, and this is the H signal. Okay, we can know that X signal can be known as the input signal, and the H signal is known as impulse response. Okay, so before we're going to code anything or run any program, we have to clear our cache first. And then after that, we're going to analyze the questions given formula. So this is the X signal expression, and this is the impulse response expression. Okay. What I'm doing here is that I separate my output into two figures, in which figure 1 will have the input signal and the impulse response, and in figure 2 we're going to have the convoluted signal, which is Y. And in figure 1, since we have to show two graphs together, and therefore we're going to get subplot. So this function enables us to plot two kinds of graph or any kind of graph in one figure. So subplot 211. What is meant by 211? This 211 is actually means that the 2 is representing the numbers of row, and 1 is representing the numbers of columns, and the 1 here is representing the order of the graph. So this subplot means I'm going to have a dimension of 2 rows, 1 column, and at the first locations of the figure. So in this subplot, I'm plotting the input signal. Okay, let us take a look how we get our input signal. From the expression here, delta n minus 2 delta n minus 1 plus delta n minus 2. We know that this n right here is the time shifting. Therefore, we can make use of this to find the x-axis location for our input signal. So we can set up n equal to 0, means that we're going to have the x-axis of n equal to 0, and n minus 1 equal to 0. We're going to have n equal to 1, and n minus 2 equal to 0. We're going to have n equal to 2. So since we already have the location, how can we know the magnitude? So when n equal to 0, it will have a magnitude of 1. When n equal to 1, I'm going to have a magnitude of minus 2. When n equal to 2, I'm going to have a magnitude of 1. So just by looking the front part of the time shifting expression right here. So we can see that x equal to 1 minus 2, 1 means that when n equal to 0, we will have 1. N equal to 1, we will have minus 2. When n equal to 2, we will have 1. And after that, we have to set the time instant for the discrete signal graph. So start from 0 to length x minus 1. So we might be confused on what is length x. So this function actually helps us to determine whether how many data we have in our x or our input signal. So if we just by looking the length x function only, we will get integer number of 3. For example, so this length x means I'm going to find how many data inside this signal. So I have the first data, the second data, and the third data. So after we code this function, the function will return the number of data. So we have 3 data right here, right? So it will equal to 3. And then we minus by 1, means we get 3 minus 1 equal to 2. Means from 0 to 2. Okay, let me explain it more clearly. So whenever we get length s, it will help us to determine how many data inside the x signal, and it will return integer type value. And then by looking how far we want our graph to go, then we only set up this value. For example, because of my x only go from 0 to 1, 0 to 2, therefore I have to make my graph end at x location at 2. Okay, usually a graph having x-axis and y-axis, right? So this length equal to 3. I have the first data right here, x location 1, second data right here. Oh, sorry, since it starts from 0, right? So the first data will right here, and the second data will right here, and the third data will right here. So when x equal to when n equal to 0, I will have 1. When n equal to 1, we will have negative 2. When n equal to 2, we will have 1. But this function return 3, means it will reach 3. So if we didn't minus 1 right here, our graph will run until here. But if we minus 1, the graph will only run until here, which fulfilling the requirements of our graph going from 0 to 2. Okay, this is how this length x or this whole expressions is talking about. Okay, so after that, I'm going to plot my graph by having stem function, which acts against n1, and this n1 is the time instant for my graph. And after that, I set my graph into red colors, and the width of my line is set into 1.5. And after that, we declare the title, declare the x-axis, and open the grid, turning on the grid. So after that, we're going to plot our impulse response. So what's happening inside the response right here is that we need to do the same things again. So we have an expression for impulse response, which is un minus 3, right? So what can we do right here is that n equal to 0, n minus 3 equal to 0. And n minus 3 equal to 0, and we can do our moving the unknown, and then we will get n equal to 3. So when my n is equal to 3, I will have a magnitude of negative 1. When my n is equal to 0, I will have a magnitude of 1 right here. So again, the graph will look like this. Okay. This is our N, and this is our Hn. So N equal to 0 right here. Okay, N equal to 3 right here. From 0 to 3, we're having 1 and 2 inside, right? So 1 and 2. And by looking at this expression, we know that when N equal to 0, we'll have 1 as magnitude. So this is 1. When N equal to 3, we will have -1. Okay, but the expression didn't show how many magnitude will the first location and the second location have, right? And therefore, it will have 0 magnitude right here. And this is why H will equal to 1, 0, 0, -1 right here. It is because of this whole thing's happening. When the N is equal to 0, I will have 1 magnitude. When N equal to 1 and 2, I will have 0 magnitude. When N is equal to 3, I will have -1 as magnitude. Okay. And then I'm going to declare again the time instant for my impulse response. And after that, I plot my graph using stem function and declare the title and the label and turn the grid on. Okay, this is what happening in figure 1. So if I run this code, I will have some output like in figure 1. Okay, we don't touch the figure 2 first. So this is the figure 1. Okay, I will have one graph right here, which this is the xn, and this is the hn right here. This is subplot. Okay, 2, 1, 1. This is subplot. 2, 1, 2. I'm sorry about my words, is a bit ugly because I'm writing using my mouse only. Okay, these two representing, I have 2 row. Okay, 2 row. Let me change colors. Okay, 2 row right here. Okay, right, it's 2 row. And then this one means that I have 1 column. And if this is 2, means that I will having another 1 column right here. So we can see that this is 1 column, this is 1 column right here. And then this one right here is means that this is the first location and this is the second location. Okay. And after that, we're going to make a new figure for our convoluted signal. So what's what we are doing here? Since we're going to plot a convolution graph, we have to find the convoluted signal, right? And how can we find it? Okay, we can find it by using this function, conv bracket. Inside will have 2 variables. This x representing the first input signal, and this h representing the second impulse response. By having this function, MATLAB will help us calculate automatically. Okay. And after that, we set it equal to y, and then we set the time instant, and then we plot it with magenta colors and 1.5 line width, and declare the titles and x labels and open the grid on. So this is our result. This is the input signal. This is input response. This is the convoluted graph. So look the same, right? When x equal to 0, it will have 1. When x equal to 1, it will have -2. When x equal to 2, it will have 1. When x equal to 0, it will have 1. When x equal to 1, it will have 0. X equal to, n equal to 2 will have 0. And n equal to 3 will have -3, -1 right here. And then this is the convoluted graph right here. Okay. So let us go 2.3a. So 2.3a, basically the things are just the same, but we have to find the first 20 values and use the subplot commands, which kind of similar to my 2.2. And then we need to set the a variables and then a big N right here. Okay, let us take a look. So still the same, we have to clear our cache before we code our program or run our program. And therefore, we need expression like this. And after that, we set up our time instant n equal to 0 to 20, and the a is equal to 0.9. Okay, why I'm setting a equal to 0.9? Because that doctor have already changed the questions, which require us to set a equal to 0.9. Okay, so for figure 1, the same things happening right here. I use subplot to plot my input and response, input signal and impulse response, and then having figure 2 to have my output graph, the convoluted graph. Okay, so this one I have already explained in the previous questions, and this one also. And x1, why x1 is equal to 1, 0, 0, 0, 0, minus 1. Okay, okay. So the same thing right here. We know that this will be set into n equal to 0 and n minus n equal to 0. Since my n is equal to 5, n minus 5 equal to 0 and n equal to 5. So our range will have 0, 1, 2, 3, 4, 5. And then we're going to determine the magnitude. When n equal to 0, I will have 1 magnitude. When n equal to 5, I will have a -1 magnitude. -1, 1. And because of 2, 3, 4 is not being stated inside here, and therefore it will have 0 as magnitude. So this explains why we're having 1, 1, 0, 0, 0, 0, 0, 0, 0, 0. Hey, sorry, this is the 1. This is 0. Okay, so 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, and -1, -1 right here. Okay, let us move on to another expression. Okay, okay, this expression right here. Since this expression stated it is -n, and the a having a power of n, and therefore we cannot use this method. We are hardly using this method. Thus, we need to set an equation for our impulse response. How? We just have to declare our expression as h1 is equal to a power by -n. Okay, why not n? Why we use -n? It's because of the -n is inside this part, and therefore instead of get our a power n, we need to a power -n. Okay, a power -n, and our a is equal to 0.9. Okay, and after that, we set the time instant for both of our graph and declare the titles and labels and turn the grid on for both our graph and also plot it with stem function. Okay, sorry, stem function. And on the figure 2, the figure 2 will have the convoluted graph or the output. And we're having CONV X1 H1, which we're going to use MATLAB to calculate for the convolution X1 and H1 and return it as Y1. And after that, we set the time instant and then plot it out together. And then we declare the title and the label and turn the grid on. And the graph will look like this. Okay, this is our graph. So 1, 0, 0, 0, 0, minus 1, 1, 0, 0, 0, 0, minus 1. Exactly the same things as I said, right? And then the graph right here is represented by this part. So what's happening right here is actually because of we set our H1 is equal to a power minus n, and our n will have a range of 0 until 20, right? Okay, from 0 until 20, from 0 until 20, 0 until okay, 0 until 20. So the 0 will stop at here until 20 will stop at here. Means that when n equal to 0, I will start my n right here. When n equal to 1, I will start my n right here. When n equal to 2, I will start my n right here. Okay, so now we're going to take a look on 2.3b. So 2.3b will have the equation like here, like this, equation like this. This is the input signal, this is impulse response. So what we're going to do is the same. We separate into two figures, and the figure 1 will have two signals inside, which the input signal and the impulse response. And the figure 2 will have the convoluted signal. Okay, so for the input signal, since we don't have any like hints to find the time shifting, and also there will be one n elements inside the expression, and therefore we're going to make our expressions into MATLAB. So we declare x equal to minus 0.5 powered by n. Okay, please note that we have to bracket this value up. If not, it will going to run a different value. Okay, and then we set the time instant, plot the graph, and declare the title, the labels, and turn the grid on. Okay, for our H, the impulse response, since the impulse response show the time shifting expression inside here, and we set n equal to 0 having magnitude 1 and equal to 1 having magnitude of -3. So we declare it as H equal to bracket 1 spacebar minus 3, and then we declare the time instant, we plot the graph and declare the title, declare the labels, and turn the grid on. So for figure 1, we done already. Okay, for figure 2, the same things. We need to make these two graphs undergo convolutions, and therefore we're having this function right here. And we just stuck our x and h inside this function. Okay, and after that, we declare the time instant. After that, we plot the graph and label the titles, label n, and turn the grid on. And we just play, or we just run. So this is our result, right? Okay, so as you can see that when the x having this expression, it will show the result like this. Okay, since our n having a range of 1 equal to 20, therefore it will keep changing. Okay, and also for our impulse response, you will have 1 and -3. Okay, this 1 and -3 is located at n equal to 0 and n equal to 1. So for n equal to 0, I will have 1 as magnitude, and n equal to 1 will have a magnitude of -3. So after both of these two graphs undergo convolution, and this result is produced. Okay. So question 2.4, doctor said that we don't have to do it, so I will just leave it blank. Okay, so this is my presentations, and thanks for patience on listening this demonstration.